We start today's lesson. I just handed out project 3. And so the idea for this project is you're supposed to find the volume of some pieces of candy using calculus. So you want to sketch a graph of a generating region that's going to be rotated around an axis to form your piece of candy. Okay, so you're going to sketch a graph that you can rotate around an axis to form your piece of candy. Show the setup of the integral that you use to determine the solid, and you can use your calculator to actually calculate the integral. And then you can eat the candy if you want. And you have to do 4 pieces of candy. We have some Lindt chocolate truffles. Isn't this scrolling? Come on. There we go. Some Lindt chocolate truffles. I have a couple of other different shapes. This is sort of, you never know what kind of shaped candies you're going to find in the store. So this is just a, whatever I find. And then a Hershey Kiss and a Reese's Peanut Butter Cup. So let's give some of these out. Okay, so we're going to continue talking about volumes of solids today. The beginning of this section is concerned with finding volumes of solids with known cross sections. These are typically hard cross-sectional volumes. Okay, so we're going to start out by finding the volume of the top 2 feet of a 10-foot diameter sphere. So like the cap on a sphere, like the top of a pumpkin that you'd cut off, something like that. Okay, so if I draw a sphere, I'm just looking to find the volume of this cap. So ignore all the rest of the sphere. I just want to find the volume of this cap. So I'm just going to get rid of this. And the base of this cap is 2. Because it's the top 2 feet. So that's 2. Does that make sense? So if I put the whole sphere back, right, it's a 10-foot diameter sphere, which means it's a 5-foot radius. So this would be 3 feet up to the cap. All right, so I'm just going to redraw the cap over here. So I'm going to pick sort of any random spot. Like, what are the cross sections of this thing? If I slice it horizontally, what do the cross sections look like? Discs, yeah, circles. So my cross section is going to look like a disc. And to find its area, I need to know that radius. Okay, so let's pick, here's a vertical line that just goes up to the top of my sphere. Pick a random spot there, and I need to find the radius to the edge of my cap. And I know that this radius is 2. Radius of the base is 2. So we could call, let's call the distance from my random spot here to the top a height of h. Then what would the distance from this random spot I just picked to the base be? Yes, 2 minus h. No, the radius is not necessarily 2. Right, okay, sorry. This radius is not necessarily 2. The height there is 2. The radius is not necessarily 2. So I have to draw this actually in the sphere. You'll find that in this geometry section, I'm terrible at drawing, and sometimes I have to redraw things a few times. Sorry. Okay, that's 5. That I don't know, but I know that this is 2. So you can see it by the looks in my picture that they're not actually the same. All right, so what I'm going to do is I'm going to sketch like a 2-dimensional picture of what's happening here on the XY plane, like slice this sphere right down the middle so I can look at the middle of it 2-dimensionally. So I'm slicing it vertically right down the middle. And what I get is this is the center of my sphere, and I'm picking some random place here to be my height h. And what I need to know is what is the radius there. And I know that the radius of everywhere is 5 for my whole sphere, because it's a 10-foot diameter sphere. And then this distance from this random spot x down to the center would be 5 minus h. I know that the height of this thing is 2, but I'm sort of picking a random spot between the base and the height. Does that make sense? Okay. So I'm letting this be h. And then that would leave this distance to be 5 minus h. Okay, so now I can use the Pythagorean theorem to get what x is. Okay, so because my cross sections are perpendicular to the y-axis, when I take the area of my cross section, here's my cross section. I should call this a horizontal cross section. It's got a radius of x. And then the thickness of this circle, not this circle, this circle, the thickness of this circle, when I slice this horizontally is going to be dh, right? Because I'm measuring this vertical distance in h. Delta h. All right, so I need to have only one variable here, h, right? So you always use your height or your width variable as your only variable. So I'm going to use h as my only variable. So I come back to this picture and I'm going to say, well, 5 minus h squared plus x squared should be 25 from the Pythagorean theorem. Solve for x, and you get radical 10h minus h squared. And then the volume of this slice is pi times the radius, which is x in this picture, squared. And x is radical 10h minus h squared. And when I square it, the radical just goes away. Okay, so lastly, I now know what all my cross-sectional volumes are. Oops. Delta H multiplied by the width of the disk. I know what all my cross-sectional volumes are, and then I'm going to stack them up and add them all up. So what would my bounds of integration be? I'm going to stack these starting where and going to where for values of H. Zero to 2. Very good. So my total volume will be an integral from 0 to 2, where I'm stacking up disks that look like that. So I'll pull the pi out, and I've got 10h minus h squared dh. Delta h becomes a dh when you go to an integral. And if you evaluate that, you end up with 52 pi over 3. So this is not very dissimilar from things that we've done in the past several classes. We just weren't given a sort of set of axes. We had to decide what would be useful in putting this thing into an XY plane. All right, so in general, the volume formula for a cross-sectional area of a solid perpendicular to the x-axis would be the integral from a to b of a of x dx, right? A of x is just the cross-sectional area. Okay, so this is where we're going to start making things a little bit different. We want to find the volume of a solid whose base is the region inside the circle x squared plus y squared equals 4. So that's the base of my region. I can graph that. X squared plus y squared equals 4 is just a circle of radius 2. So this is the base of a three-dimensional object. So there's a third dimension to this thing, and this is only a two-dimensional board, so this is difficult for me to draw. But you're going to imagine the cross sections of these things perpendicular to the x-axis. So here's my x-axis. I have to draw these things perpendicular to the x-axis in the third dimension. So like coming out of the board. Are squares. So I'm absolutely terrible at drawing this. I'm not going to try. I will show you a little animation. Okay, so here is a circle. Sketched just the base. This one happens to be a circle of radius 1. And then I'm going to draw squares coming out of the board on top of this circle. And you get a solid that looks kind of like this. So you can see the base is down here in the XY plane. And then this is the Z plane where I drew squares. Or Mathematica drew squares coming up out of the base. So that's what you want to imagine. You say, okay, I'm going to look at a random spot in my base and imagine drawing a square. That's going to be one line of the square, and then there's going to be a square coming out of the board, right? So all four sides are going to have the same length as this pink line. So I've got a square coming out here. And then I'm going to stack these squares up, add them all up. Okay, so this is just my base. And then I can look at my cross sections, which are squares. Okay, so what I need to know is if I call this distance x, right? Just pick a random spot along the x-axis to draw one representative cross section. I say I'll make that at x. Then I need to know this distance, right? I have to be able to use x to figure out how long this pink line is. Any ideas? Yep. X is the distance from 0 on the x-axis. Yeah, sure, we could do the Pythagorean theorem. We know what is the radius of this thing? 2. So I could say x squared plus 2 squared equals, this is, oh no, sorry, 2 is the hypotenuse. X squared plus y squared equals 2 squared. We kind of already knew that because that's the equation of the circle, right? That's y, that's the equation of the circle. So if I wanted to know what y was, right, we can call that y. Just solve this equation for y. So y would be the square root of 4 minus x squared. So my square is going to have a base or a side length that's 2y. One up and one down. So this would be 2 times the square root of 4 minus x squared. And it's a square, so all 4 sides are the same. And it's got this square has some little thickness. And what would the thickness of that square be? There's no h's in this picture. Which variable is it? Delta x or delta y? X. Yeah. Yeah. Because I chose a random x to draw my square, right? And if I make that square have a little bit of thickness, that is a x measurement, would be the thickness of that square. Okay, so the volume of this slice, or the volume of my cross section, is going to be length times width, base times height for a square. So it's going to be 2 square root of 4 minus x squared squared. Side length of a square squared gives you the, and then the delta x. Which I could simplify this to be 4 times 4 minus x squared. Square the 2 out front, and then when you square the radical goes away, and you end up with 16 minus 4x squared. All right, so now I have all these squares. I'm going to start right here. I'm going to make a little square popping out of my board. And then I'm going to put another little square here and another square here. And I know how to find the volume of each of these squares, and I want to add them all up. So that means take an integral. And I'm going to start where and end where and adding up these square volumes. -2 to 2. And each square is going to have a volume 16 minus 4x squared dx. All right, so just a quick remind you, I know you all know how to do this, right? But take an antiderivative, then plug in the bounds. So the antiderivative of 16 is 16x. The antiderivative of 4x squared is 4x cubed over 3, evaluated from -2 to 2. So that means plug in your 2, then plug in your -2, and subtract them. Okay, and you end up with 128 thirds. Okay, so I think that we should take a minute to use some technology to visualize this much better than I have drawn it. All right, so here is our base, circular base. We're having a -2 to 2. So this is a circle centered at the origin, radius 2. So here are the chords. These are just my slices upon which I'm going to build squares. So the way we're looking at this right now is like a bird's eye view on the base. So on each of these chords, each of these slices of my circle, we would build a square coming out of the board to create a solid. So here's the great thing about technology. We're going to rotate this. So now you can kind of see this in 3 dimensions. Now this is the x-axis stayed the same. The y-axis we dropped flat. And now this vertical axis is the z-axis. So we can draw this in 3 dimensions. So on each of these chords, I'm going to build a square. So you can see there's 4 sample squares that I built on each chord. Okay, and then we can rotate it back. It's helping you visualize it better than my terrible drawings. The squares are built off of the chords that are the base of the circle. All right, we'll sweep 1 square through so you can see what happens. Square gets bigger and bigger and bigger, and then smaller and smaller and smaller. And we're going to stack all these squares up. So here's the solid. So that's what the final thing looks like. Circular base, square cross sections. And then there's my original 4 squares that we were using to visualize this. And there's our sliding square within the solid. So this says that the volume of this solid with a radius of 2 square cross-sectional areas is 42.67, and that is the same thing as 128 thirds, or it's 128 thirds rounded to the nearest hundredth. Is that good? Okay, so this problem is going to be exactly the same as the last question, but the cross sections, instead of squares on those chords, I'm going to build equilateral triangles instead of squares. All right, so I'll start by trying to kind of draw this for you, because you're not going to always have this technology at your fingertips, so you have to be able to kind of visualize it. Start by drawing something. So my base is a circle of radius 2. I'm going to pick a random chord on here, just like I did for my squares. Give it a little bit of width so that you can see that the cross section is going to have width delta x, and we're going to put this at a random x value between -2 and 2. And this time, instead of building a square coming out of the board, I'm going to build an equilateral triangle. So I'm going to build a 3-sided figure where all 3 sides have this distance that is the pink representative rectangle. So just as before, right, if this were y, we came up with y is the square root of 4 minus x squared. Because it's the same base, we get the same size of the rectangle. But then my cross sections are different. My cross section is now an equilateral triangle. And this base is on that chord. So I just sort of plucked that out and drawn it in a different orientation. And I know that this distance is 2 times the square root of 4 minus x squared. 2 because this is y, and I'm building this on a sort of a double y, the top part and the bottom part. Okay, so I need to find the volume of this cross section, and this cross section is going to have some small amount of depth, and that depth is delta x. So the volume of this cross section what do you think? No, it's not y, because, okay, so yeah, the volume of any sort of prism, which is what this is, a small prism, is going to be the area of the base times the height. Right? The area of the base will be the area of the triangular face. Height will be delta x. So I need to find the area of an equilateral triangle. So let's take a minute to just think about the area of an equilateral triangle without all these crazy variables. So you were thinking that this height, because the area of a triangle is generally given as 1/2 base times height, but this is y, or this is 2y, this is 2y. So why do you think that height is y? Yeah, it's going to change at the same rate, but it's not the same. Yeah. Yeah, it would be z. Yep, but yeah, that would exactly be z. We have to figure out what z is in terms of y. So let's take a little aside here. Let's say we have an equilateral triangle, and its base we'll call s. So all 3 sides have length s. What are all 3 angles? 60 degrees, because the 3 angles of a triangle have to add up to 180. Since this is equilateral, all 3 angles are the same, so they're 60 degrees. So if I drop a perpendicular here, this would become s over 2 and s over 2. So I'm using s for side length, and maybe I should have picked something else, I don't know. Okay, so the area of this triangle will be 1/2 base times height. My base is going to be s, right? And then I need to know this guy h. We could use trig, or if you remember high school geometry, the 30, 60, 90 special relationships, you'll get the same thing either way. Right? So what would you do if you were going to use trig to find out what h is? Yep. So h squared plus s over 2 squared should give me s squared. Pythagorean Theorem. H squared plus s over 2 squared should give me s squared. And then I just solve for h. Okay, so h squared is going to be s squared minus s squared over 4. Okay. What is s squared minus s squared over 4? 3/4 s squared. Because 1 s squared minus a 4th s squared is 3/4 s squared. Then just square root both sides. square root of 3 over 2 times s. So it's 1/2 times my base, and then my height is the square root of 3 over 2 times s. If I simplify this, I get radical 3 over 4 s squared. So now we have a quick and easy formula for the area of an equilateral triangle. If you know one side length, you just do root 3 over 4 times that side length squared, and you have the area. We could have done all of this same work using the variables we had. It just would have gotten messy, right? So I just thought it would be simpler to derive this formula and then use it. So radical 3 over 4 s squared. So we'll come back over here, write that down. My side lengths here are now 2 times radical 4 minus x squared. So when I square that, I get 4 times 4 minus x squared. There was a root 3 over 2. That was the height. And then when I plugged it into the area formula, I had a 1/2 times a root 3 over 2, 1/2 base times height. So that made it root 3 over 4. Okay, so these 4's will cancel. And the volume of my cross section ends up being 4 root 3 minus root 3 x squared. Sorry, these are missing delta x's. So it's finding the volume, not just the area of the base. All right, so finally, I can find the volume of my entire solid by adding up the volumes of all these cross sections of very small width. So my volume of my solid is going to be an integral. So I'm going to add up a whole bunch of these little cross sections from -2 to 2. And they're going to all have volume 4 root 3 minus root 3 x squared dx. And if you just plug that into your calculator or take the antiderivative and plug in your bounds, you end up with approximately 18.475. All right, should we check our work? Use the sketch pad. So this time, same setup. I have a circle, base that is the base of my solid. It's got radius 2. I'm going to show the chords. Okay. On each of these chords, I'm going to build an equilateral triangle sort of sticking right out of the board. So in order to be able to draw this, I'm going to drop the y-axis flat, and then I can draw these equilateral triangles on each chord. So there's 4 representative equilateral triangles. Rotate that. You can see them. Sweep one through and try to get an idea from sweeping this through what the solid's going to look like. So there it is. Solid. There's my 4 triangles within it. And they said the volume is 18.48. which is what we got, 18.475. Everybody got this one? Okay, do one more of these together. Okay, I want to find the volume of the solid whose base is this right triangle. And I graphed it in the xy plane. It's tough to see, but there are xy axes there. It's graphed in the xy plane. And this is its base, and its cross sections are perpendicular to the y-axis. So they're going to be coming out of the board, but they're going to be perpendicular to the y-axis and not the x this time. Are semicircles. So it's going to be like, if I pick a random spot here, I have a semicircle coming out of the board, perpendicular to the y-axis. So at each of these spots, a semicircle. It doesn't look so bad. Okay, so my cross sections look like semicircles, right? And they're going to have some small amount of width. And the volume of my cross section for a semicircle is always going to be pi r squared over 2. Semicircle. So the question is, what is the radius of this thing? We're in the xy plane, so we should deal with x's and y's as our variables. When I create these semicircular disks, and they're going to have some amount of width here, which variable is going to represent the width of that semicircle? Delta y. So if I'm drawing one of these semicircular disks, we'll call this at a random height of y. Then this distance x would be the diameter of my semicircle, and I need to be able to relate the x and the y, right? I think it will be clearer if I just draw one of these. So here's some random height y. What I need is that distance x, because that x is going to be the base of a semicircle. So if I know y, can I find x? How would you do it? I could find an equation for that line. Yeah, that's a good idea. That's not how I did it. Anybody have a different approach? I did similar triangles. Yeah, either way. And this line is easy, right? It's got a y-intercept of 3 and a slope of -3/4. So you could just plug in, just solve that thing for x, that line. -3 times -4/3. There you go. So that's one way we could get x. Another way would be similar triangles, and I would say, well, if this distance is y, the rest of this distance is 3 minus y. So then I would do small to big of the two triangles. Small height would be 3 minus y compared to the height of the entire big triangle, which is 3. Base of the little triangle is x. Base of the big triangle is 4. 3x equals 12 minus 4y. X would be 4 minus 4/3 y. Same thing as you would get up here. -4/3 y plus 4 when you distribute the -4/3. So you can do either way. All right, so if this is x, my radius is actually half of that, because that's the diameter of the semicircle. So my radius, r, is going to be 2 minus 4, 2 minus 2/3 y. Squared over 2. So this would be 4 minus 4/9 y. That's not true. I can't believe I just did that. It's like my biggest pet peeve mistake that all of you make, and I just did that. I had these two things, and I was just going to square both of them. I'm just going to leave it as it is. Okay, and then the volume, I need a delta y here. All right, so then my final answer is going to be an integral. Right? The volume of the solid is going to be a bunch of these semicircles stacked up, right? Like this. So I'm going to start where and end where? I'm stacking these. 0 to 3. I'm stacking these up along the y-axis. 0 to 3. So the answer, the total volume, is going to be an integral from 0 to 3. Each semicircle is going to have volume pi times 2 minus 2/3 y squared over 2 dy. So I could pull out the pi over 2, right? And then I could work on taking an antiderivative of that thing. And you end up getting, oh, I don't want to waste the time just finding integrals. You end up getting 2 pi. All right, let's look at a quick picture of this. Here's my right triangle. This one's a little bit different because I built it under the x-axis, but it's got the same shape. So we have a 4 here, 3 here, and I'm going to build semicircles perpendicular to the y-axis. So here are my segments perpendicular to the y-axis. I'm going to build a semicircle on each one. But in order to be able to draw that, I'm going to drop the y-axis flat. There's 5 representative semicircles. Just show one semicircle sweeping along the base of the region. Create the solid. It's kind of like a tunnel that's getting smaller and smaller and smaller down to a point. Yeah, half a cone. So there's my solid. There's the 5 semicircles within it. And it says that the volume is 6.28, which is 2 pi. Okay, I'm going to pause here because I've been talking for a long time. First, I'm just going to point out the next thing in the lesson is the arc length formula. And it's just a formula, right? And I had planned to kind of derive it and show you where it comes from. It's all written out right here. So if you want to read where it comes from, feel free to do that. But it's just a formula that you plug stuff into, right? So it's the integral from a to b of radical 1 plus f prime of x quantity squared. So that is the arc length of the curve f of x from x equals a to x equals b. So you would have to take the derivative, plug it in there, plug in your bounds, and then just calculate the integral. And there's a parametric version too. So if your curve is defined parametrically, you use this one. All right, but that part's easy. It's just plugging into a formula. This is harder, so I think I'd like to go over it with you. Okay, so I have the base of my region is the area bounded by y equals x squared, the x-axis, and x equals 1. So if I just draw a quick sketch of that, x squared, x equals 1. That is the base of my region. And then I'm going to build equilateral triangles all along here, perpendicular to the x-axis. So I'm going to pick a random x here. That's going to be the base, and then I'm going to build an equilateral triangle on top of that base. So it will look like that. Okay. And then I need to know how high that is, which is what? The length of that purple line. X squared, yeah. At any x value, you can find the height there by plugging into the formula for that curve x squared. So that is the side length of my equilateral triangle. All three sides are length x squared. And this thing is going to have some small amount of depth. And what would that be? Delta x. Yeah. Because the base is going to have some width like that. Delta x. Okay, so then the area or the volume of this thing, volume of this slice, is going to be, remember, s squared radical 3 over 4, where s is the side length of your equilateral triangle. We derived this a little earlier. So I'm going to replace the s with an x squared, and I'm going to get x to the 4th. Radical 3 over 4 delta x. Right, the side length of my equilateral triangle is x squared. So then finally, I'm going to stack up a whole bunch of these equilateral triangles along the x-axis from 0 to 1. So my final volume will be an integral from 0 to 1. That's the sum of a whole bunch of triangular prisms of very small depth. And it would be radical 3 over 4 x to the 4th dx. And that is not too bad of an integral to calculate. And you get radical 3 x to the 5th over 20, evaluated from 0 to 1, which is radical 3 over 20, just approximately square root 3 over 20.0866. Okay, that's it.